So yesterday I talked a little bit about random tensor networks and the connection to gravity with these fixed area states. So today what I'm going to do is try to apply that idea and so this connection between tensor networks and gravity to learn something about gravity just by using those tensor networks. And so in particular, the problem that I'm interested in is trying to understand measures of multi-party entanglement, which are information theory measures that measure entanglement between different parties. And a particular theme of this story will be to go beyond just the RT formula, which measures two-party entanglement. And there's a nice bit thread story, which sort of is equivalent to the RT formula. And we'll sort of see how these things change as we go to multi-parties. So this is based primarily on a set of papers that we wrote with Chris Akers, Tom Faulkner, and Simon Lin, the last of which is to appear soon. And that will be for a portion where I talk about the reflected entropy. And there's also some other upcoming work with Zhidong and Jonah Kudler-Flam, which will be about entanglement negativity. So these will be the two primary things that I'll be talking about. I'll also allude to some other work with these collaborators. Okay. Okay, stop working. Okay. Okay. Good. So let's start with just understanding two-party entanglement. So that's something that's reasonably well understood at this point in terms of the Ryu-Takanagi formula. So as I was reviewing yesterday, the Ryu-Takanagi formula says that the entropy, entanglement entropy of region capital R is computed by the area of this extremal surface gamma R, which we'll call the HRT surface. And the entanglement entropy is sort of the ideal, I mean, it's the unique biparty entanglement measure. Like when you have one pure state and you just want to measure the entanglement between two parties, the entanglement entropy is pretty much the unique thing that you need to know in order to measure the entanglement between them. So the RT formula pretty much characterizes everything that we'd like to know about two-party entanglement in holographic states. And there's a sense in which the entanglement is geometrized in the sense that the entanglement entropy is measured by some area in the bulk. And so in a sense, you can think of this as the emergence of this geometry from the existence of entanglement. So the presence of this entanglement is being seen, is being probed by the presence of some area in the geometry. Yeah. What I mean by unique is like, so essentially, the way information theorists think about it is like you want to quantify what you can do with the entanglement entropy. So you want to do some tasks, like for example, do some teleportation or something like that. Every such task is pretty much characterized by the entanglement entropy. There's the subtlety that I'm talking about is that when you go to higher parties, there's a difference between classical correlations and quantum correlations. But when you just have a pure state, then everything is quantum entanglement. So there's just one thing you really need to measure.
No, what I was asking was, why do you also include any kind of...
Oh, I see. Good. So I think when people say that, so again, like this is something I was alluding to yesterday, which is the entanglement entropy satisfies a nice continuity bound. So it's relevant for physical processes. The Renyi entropy in that sense is something that's unphysical. It's often easier to compute. But it's unphysical in the sense that if someone just added some small noise to your state, like the Renyi entropy can totally change. So it's unstable. So when someone measures things in a lab, like
then there are no physical properties which rely on the stability.
There's no operational tasks which rely on it, because in operational tasks you're always allowing yourself some error and so on. Yeah.
So I thought that somehow the set of all correlators of local operators in this region A is encoded in the density.
Yes.
So I would have thought that all eigenvectors of the reduced density matrix are involved and not just one.
Oh, okay. That's fair, but I think that's true. But if you're just interested in what So if you just had these two systems, R and R bar, and if you were just interested in what sort of tasks you can do with the presence of entanglement, so I give you system R bar, I have system R, and we're allowed to do whatever we like with our systems, but we have to communicate in some way. In that sense, the entanglement entropy is the only relevant measure, because if I act with some unitaries on my system, it'll change the correlation functions on my system. If you act with some unitaries, it'll change your correlations functions and so on. But the only thing that's important for communicating, so let's say doing a teleportation protocol, is the entanglement present between us. Any local operations that I do or you do don't affect that. It's true that if you care about correlation functions, then the density matrix is important because you care about the basis as well, not just the eigenvalues. But here I just mean in the sense of quantifying the entanglement between these two parties.
Another way to put it is, if you use, this is towards distillation, is that if you wanted to use the number of Bell pairs you can extract from local operations as a measure of entanglement. The two subsystems, you say how entanglement. So, okay, how many Bell pairs worth of entanglement is there? Then the measure, the unique measure of that, if you do just unitaries on both sides, is the fundamental.
Well, there could be other tasks. So the answer is Rengian.
There's none that I know of, and I think it's unlikely for the reason that, well, unless the task is specified, like most of these tasks are usually like in some asymptotic limit with some error and so on. It seems unlikely to me that a Renyi entropy will ever show up in that, just because of this instability.
Classification for entanglement called bound entanglement and
Yes.
entanglement.
Yes.
And the bound entanglement is supposed to be that entanglement cannot be distilled as Bell pairs.
Yes.
But it can be distilled otherwise.
Yes.
So I'm saying, Bell pair is one criteria, but there could be other tasks.
But this bound entanglement is present when you have a two-party mixed state.
I'm just giving.
I agree. Yeah.
I'm saying there could be many tasks.
But if it's a mixed state, it is a Shannon type of contribution to the formula. You won't be able to use it. I mean, it's not a true measure of entanglement. In that
it's capturing some classical correlation as well.
Classical correlations, you would be able to do it without it.
Well, I think typically,
you can do with that. I mean,
maybe what you're saying is, in general, we should just say the entanglement spectrum is what characterizes the. I think, okay, that's fair. I just think this continuity makes the entanglement entropy special as well. And
but this discontinuity is because very, very high eigenvalues change. Okay, so but then don't take rho to the end, take some other way think. Just a low lying eigenvalues don't suffer from system.
You mean some other continuous function?
Just some
fair enough.
Some envelope function.
Fair enough.
Okay. The low lying you're saying pretty sensitive to
fair enough. I agree. Okay. In that sense, it could be relevant for something.
It's a mathematically well-defined object, of course, traced to go to the end. But to the extent that entanglement stands for tasks which you cannot do in quantum mechanics with just superposition. Because superposition can be done classically by waves. But there are tasks in quantum mechanics which cannot be achieved just by superposition, for which you need something more. And you want to quantify that something more. Then I think for two parties, it could be.
Well, maybe as they're saying, like the entire eigenvalue spectrum in some sense quantifies it. So any function of it.
Set for any task which you can't accommodate. If you just had two classical systems with no entanglement, then you'd be able to do anything you did with those correlations just by a classical system. I would not need anything quantum.
But the
bound entanglement is a counterexample of that, right? Bound entanglement. So that's a bigger story we can talk about. The characterization of that is in terms of whether you can distill entanglement in Bell pairs or not. Okay, and then bound entanglement is something that you cannot.
But
I use other characterization, let's say not quite Bell pairs, but let's say higher dimensional system or something like that. Then you let's say electrons with many states.
Then it would show up as proper entanglement.
You can distill.
And this is true for ballpark analysis.
Yeah, mixed.
Maybe one way to say what I was saying was that in a two-party pure state, like every correlation is quantum correlation. Like there's no difference between classical correlation and quantum correlation, really. So in that sense, like in a two-party pure state. So you just need one thing to quantify, like how much that is. You could choose some other measure, as you say, but like it's sufficient. Like if I just asked you how much entanglement, like one number is sufficient.
Okay, that's a measure, right? I don't know if the next discussion doesn't rely on it, we can go forward.
Yeah, it doesn't rely on so much. Okay, good. So, okay. So now, in order to go beyond that, let's say we wanted some finer view of geometry in the sense that we want not just these extremal surfaces anchored to the boundary. There are, for example, there are regions in the geometry which aren't probed by any such extremal surfaces and so on. So if we want something like that, and simultaneously, let's say we also want to understand the entanglement structure better on the boundary side, then we'd like to compute some sort of multi-party entanglement measures, right? So in general, characterizing multi-party entanglement is a really hard problem. So this is something that like people have struggled with for a while, and it's only really been done in the case of few qubits and so on. That's like the only situation where we actually understand how to characterize entanglement. So in general, there's like a whole zoo of measures which captures different aspects, as like, for example, what Abhijit was saying, like some things are bound entanglement, some things are not. So different measures will capture different aspects of entanglement. Some will also capture parts of classical correlation. But in general, there's a lot of them. And so it's still an open problem to understand which of these are the best things to measure, which of these are useful for certain tasks and so on. And so here, this is just a preliminary step in trying to understand some of them which have decent properties. All right. So before moving on to multi-party entanglement, there's something else I want to say about bipartite entanglement.
What would it mean to completely understand multi-party, three-party entanglement? What does that state mean? What would it mean?
Yeah, I think you'd say if I ask you about any task that can be done. So for example, the case where we've done it is like when you have 3 qubits. So when you have 3 qubits, there's 3 inequivalent ways in which they can be entangled. Either you have bell pair-like entanglement, or you have GHZ type entanglement, or there's what's called the W type entanglement. What this means is that there's a specific measure of entanglement, which is, it has this nice property that it's monotonic under what's called LOCC, local operations and classical communication. So it's something which is used for a lot of these entanglement measures. You want an entanglement. So doing local operations on my system and just communicating classically should not be able to create entanglement. So you want it to be monotonic in that sense. And then you want to measure some quantity which tells you, which classifies these systems such that under any of these simple tasks, you're not able to go from one or to the other. So in the sense in which the W state and GHZ, so basically by just applying some simple local operations in classical communication, even allowing for like probabilistic things and so on, you're never able to transform a GHZ state to a W state. That, for example, would be something something like that.
And just to understand, in that case, I'm sorry, I know so little about this multi-party. If you computed all the mutual information or all the entanglement related objects, that still wouldn't allow you to tell these 3 states apart. Is it?
Sorry, can you say that again?
You know, for example,
if you the bipartite,
A, B, and C, A union B, etc. None of that helps.
You can still have the entropies. You need something more.
In the bipartite case, does this LOCC or maybe LOCC does not preserve the spectrum? Does it preserve the spectrum?
LOCC, the spectrum is it doesn't preserve the spectrum, but there's a similar monotonicity property. Like
Yeah, there is a moment on you can destroy the entanglement.
You can destroy, yeah.
Yeah, you can do inefficient teleportation.
Yeah.
Just inefficient.
In that sense, the spectrum, I guess, is important if you wanted to do a finer classification, LUs, local unitaries, stuff like that. But if you're not interested in that, then
so it's the measurements that destroy the entanglement.
You're allowed to couple your system to other environments and stuff like that.
Which I can think of in classical terms as measurement.
Yeah.
Quantum mechanics is either
Right. Yeah.
Okay.
Yeah.
So it's like decoherence.
It's like decoherence. Yeah, you've coupled to something else and it's entangled with that now instead of your other system. So.
I have a few questions. It's very easy to come up with the state, a tripartite pure state even, which has the property that its entire spectrum of density, all the density matrix is the same, but the states are not equivalent in the sense that you can construct some local unitary invariant measures which are different numbers.
Okay. But I mean, what I was trying to say was that, okay, I need to understand it better, but okay, the point is, does it translate to, as Pratik was saying, some protocol which you can accomplish with one, which you can't accomplish with the other, although they have the same entanglement measure? For bipartite, you were saying, right? And you were saying yes. I mean, or at least it suggests what you're saying. I'd like to understand such a protocol a little bit better, because it seems very strange to me somehow, since I've only thought about entanglement with the standard protocols of, distillation dilution. So, okay. But yeah, if it's true, then it's kind of might be strange.
Yeah. Okay. Good. So another interesting story that happened in this measurement of bipartite entanglement is that of bit threads, which is essentially, you can think of, let's think about a graph version of the RT formula, which is, let's say you have a tensor network and you're just finding the minimal cut through this graph, which computes the entropy. Then there's the so-called convex duality, which translates a min cut problem to a max flow problem, something that's used in computer science all the time. And what the max flow problem says is you want to construct a flow which starts from region R and ends up in region R bar with some maximum density. So you want a flow which doesn't have local density more than some number. And then given those constraints, you want to find the maximum possible flow from R to R bar. Now, Hedrick and collaborators have showed in many different situations, I mean, for Einstein gravity, but also for higher curvature gravity and things like that, that you can just apply this convex duality and you get this bit threads picture, which is the max flow version of the RT formula, where you can just think about bit threads flowing from one region to another. And in some sense, this is like it's a pretty vivid picture of entanglement, because you can think of these threads roughly as bell pairs flowing from one region to the other. It's not literally going from one local point to another point, but still in some sense, if you apply some local unitary, you could imagine making the original state into a collection of different bell pairs which have some entanglement across this.
You should go into something I haven't understood. If you have this arising that in four parties, if you take four parties, you can't think of the entanglement in terms of just bonds like this. That is, then you have this notion of topological entanglement entropy in three of them. And if you thought in terms of bonds, at least you get zero topological entanglement every time. So, okay, as an aside, I want to ask this. I mean, are you saying, or is this idea saying that, look, I can assign some bonds like this and say, okay, if there are two bonds, there's one bell pair work between A and B, and account for all the entropy like this. Is that the picture?
Yeah, but I think, as you said, it doesn't work.
Yeah, it doesn't work in general. It's easy to show with four parties.
Yeah.
So I've not understood the big.
Sorry, so this is for two parties. I haven't gotten to multi-parties yet. So
just bipartite.
Just bipartite?
Yeah, let's consider four parties, four elements.
And
let's say you want to draw a network, just the lines like that.
Yeah.
Making sure that bipartite, all the bipartite entropies are reproduced by this picture.
All of them simultaneously. Yeah, no, you can't do that.
Yeah.
Even the bipartite.
but for more parties. You mean the bipartite measures for more parties? Yeah. You can't do that. Yeah, you can't do that. Yeah,
you can't do that.
That's right. That's right.
Not even multi-party.
I agree. Yeah, I was going to get to that, but I mean, so this is an important point. Yeah.
Only 4 parties, but you can show that. So then what is this picture? I don't quite understand.
So this picture is like, this picture is just representing, if you pick 2 parties, then you have a particular bit thread configuration going from one to the other, which is representing the entanglement between them. Now, this is not literally the entanglement because you probably have to apply some unitaries to make it look like these bell pairs. And if you picked a different choice of regions, you'd probably have to pick a different choice of unitaries. So for every choice of region, the claim of this bit thread story is that for every choice of region, you pick one max flow configuration. That max flow configuration is going to be different depending on what your parties are. So if you picked a 4-party thing, you can pick a choice of 2 parties and get a bit thread configuration, but then there's no guarantee that it'll work for the other choices.
Okay, so this is the part. Okay, that you can do, of course. That's just a way of visualizing the.
It's just a way of visualizing the entanglement. Sometimes, so good. So in computer science, very often max flow problems are much easier to solve than min cut problems, and that was sort of the motivation behind rewriting it in this way. Because, for example, some of the proofs of entropy inequalities simplify when you write it in terms of bit threads. At this point, it's just a rewriting in terms of some equivalent thing. Whether it's a heuristic picture to think about this as some bell pairs that you can extract by doing some process. That's all the claim is. Yeah.
I mean, if you take an interacting spin system,
then
the ground state has like nested bell pairs. Bell pairs of bell pairs, and
yeah.
I mean, so it doesn't look like just a bunch of bell pairs.
Yeah, that's right. So in order to get something like just bell pairs, you need something like a large parameter. So typically, when people, like in quantum information, you'd think about having many copies of the system. And then in the limit where the number of copies goes to infinity, you pretty much get just bell pairs. It's like a central limit theorem type thing. Yeah. Here, you don't need many copies of the system. You basically just have one copy, but there's like G, which like 1 over G, which is large. So it's effectively because of that. Like there's a sharp peak. I mean, the spectrum is pretty non-trivial. It's not just like at one point, right? Like as I was drawing yesterday, there's some sort of thermal spectrum in the entanglement. But there's a sharp peak. So pretty much if you look near that peak, you have like bell pairs. Yeah. Okay, good. So related to what you were saying, so you can take this picture and try to look at 3-party entanglement. So for 4-party entanglement, there isn't one particular bit thread configuration which like can simultaneously give you all the right answers. But for 3 parties, there is, and this is a non-trivial fact. There was no reason this had to exist. So these authors had taken this as motivation to conjecture that the entanglement structure of either gravity or in tensor networks and so on is mostly bipartite in the sense that you can apply local unitaries on these 3 regions and extract these bell pairs, which they expected to basically correspond to this non-trivially existing 3-party bit thread structure. That was their conjecture.
Yeah, this is too much. I mean, by the way, if you're sorry, you should go on, but the obstruction, if you have 4 parties, to being able to do this is a very beautiful quantity. It's the topological entanglement. With 3 parties, you can define the topological entanglement. If that's non-zero, you can't describe the bit thread picture with 4 parties. So why would they expect that to? Does that vanish in gravity cases?
For 4 parties?
Yeah. Why did they expect for 3 parties that it?
No, they showed this. They didn't expect this.
Well, I was thinking in gravity, you have many regions, the boundary can be broken up into arbitrary pieces.
Yeah.
So, okay, but sorry, I misunderstand. If you break it into 3 pieces, then you can do this, is the point. Into 3
sorry, when you say pieces, you mean like you can have, like each of these subregions can be like multiple intervals. It doesn't have to be like one interval.
But you're only caring about the entropy.
Yeah, yeah. We only care about the entropy between A and C, B and C, and A and B. That's it. That's yeah. Yeah, so in the sense of within these three parties, the structure is of some well pairs shared between A and C, some between B and C, and some between A and B.
Yes.
That's and in fact, in a paper by Nizami and Walter, they showed that this was precisely true in what are called random stabilizer tensor networks. So similar to what I talked about yesterday, random tensor networks were where we picked the vertices to be random, Haar random tensors, and a sort of simpler version of it is these random stabilizers. So stabilizers are basically like Clifford gates. So you basically pick random. For now, you can just think about these as less random states than the Haar random states that we picked yesterday. They're basically two designs, and
this is
yeah.
If A, B, and C together are a pure state,
Yeah,
then you can always do this.
there's no I mean, for a GHZ state, you can't do this.
You can't.
A GHZ state is.
No, I mean, I can always, yeah, okay, then maybe this is, I can always get away with a picture like this and get all mutual entanglements, right? You know,
So the meaning of this picture
No.
is that, I mean, one tacitly breaks up A into A1 and A2, B into B1 and B2 and C into C1 and
so
C2.
tensor product tables.
Yeah.
Yeah,
Then A,
Oh.
some part of A is entangled with
Okay.
some part.
yeah.
No,
That's what it means by mostly bipartite.
that's what we.
Yeah.
Bipartite is this and that. Nothing else.
Yeah, now I didn't understand. So the idea is each of them is a tensor product.
Yeah, you can split it into a part which is entangled with C and B and so on.
By part you mean, okay.
Yeah.
Not just describe
And the path that is entangled with C is not also entangled.
Not also, it's like a product structure. Yeah, so that's why they're products of well pairs.
That's a much.
Yeah. And okay, good. So in these random stabilizer tensor networks, which are less random than the random tensor networks, you can actually show that this is precisely the structure of entanglement that you get. So this was some more evidence that they had for the fact that maybe holography has this mostly bipartite entanglement structure. Okay.
But does this mean that in gravity, any non-trivial measure of tripartite entanglement must be zero?
This was the conjecture. I'll tell you that that's wrong. Yeah. Okay. All right. Good. Okay. So yeah.
So the bit thread picture basically says that the bit thread cannot split.
The bit thread, yeah.
One point
It's
in some interval has to end up in only one.
Yeah. It's a flow which is going from one side to the
So
other.
that's
Yeah.
what this last point is about.
This one.
Yeah, the mostly bipartite.
Yeah, exactly. I mean, so there exists some configuration which will simultaneously give you one. So here we just drew a bit thread configuration which gave you the right entropy for two regions. But here you can draw like one bit thread configuration on the geometry, which will give you the correct entropies for A, B, and C. All of them. Which is a non-trivial fact, which you can't do for four parties, as Sandeep was saying.
And this is true even if each of these parties have minus.
Yeah. But as long as you're not careful about what the entropy between them is, like all you care about is, so it's like a pretty general fact.
Mostly means to good approximation.
Yeah, that was their. I mean, this is how. So this is how we interpreted what they said. Like they basically said this exists. It should be like bipartite. The way we interpreted it is to say that the state, to some good approximation, in a decent measure of distance, should be rewritten as something like this up to local unitaries. Like that I think is a easy reading of what they say.
Thank you. I think is it fair to say the following that
Yeah.
if you give me three parties,
Yeah.
right? Then and you only allow me to measure the bipartite entropy, let's say
Yeah.
entanglement entropies. Then this answers
Yeah.
can solve for that. Because you have three variables. In
Yes. Basically. So the number. Exactly. So there's three parameters because you want the three entropies, and the red stuff, blue stuff, and green stuff is like matching those parameters. It's still non-trivial to show that such a flow configuration exists and so on, but like roughly that's the idea. Yeah. Okay, good. So let me give an overview of today's talk. So what we'll try to do is analyze two particular multi-party entanglement measures. The first being the reflected entropy, where and we'll be analyzing each of these in tensor networks. So just to show you that tensor networks teach us something about holography. So firstly, for the reflected entropy, it's the calculation of reflected entropy actually turns out to be pretty, the analysis turns out to be pretty complicated on the ADS-CFT side. But on the tensor network side, we can actually provide some rigorous results, which give more motivation for the holographic proposal for reflected entropy. And we'll also come close to relating it to bit threads and show precisely how or where it failed. So the thing that I told you just before this about this mostly bipartite conjecture is proved wrong by using this holographic proposal of the reflected entropy. But it wasn't so clear before this why exactly it failed, or at least like one attempt here will be to come close to showing what step went wrong. And the second thing I'll be talking about is the entanglement negativity, which is another measure of quantum correlations between either tripartite pure states or bipartite mixed states. And in this context, we'll demonstrate that the naive replica trick that was done previously in ADS-CFT was in fact incorrect. And there is this feature of replica symmetry breaking, which is motivated by tensor networks. And firstly, I'll show you how we see that it's broken in tensor networks, and then argue for how to see that it's broken also more generally in holography itself.
So you will demonstrate that that picture is an incorrect representation of the actual quantum.
Yes, that's right. That's right.
So Pratik, by multipartite, you mean tripartite?
Yeah, in this context, it's just tripartite.
But do you have any more partite measures?
Well, I mean, there are the measures you wrote down. Like I mean, there's many measures you can.
These measures are not generalizable to higher parties, right?
These, well, negativity, no. Reflected entropy, maybe, as we were discussing yesterday a little bit, like you can have some multi-party measure for that. But at this point, I'll just be talking about this. Yeah.
I'm really sorry to just go on top. To make the notion of mostly bipartite precise, do you have to work in asymptotic limit where the dimensions of
you don't. So you can, I mean, there is a large parameter here, which is 1/g. So all you need is that the distance in some appropriate metric is parametrically small in G. That gives you some small number to.
Simplistically, for example, each of the three could have been three-dimensional Hilbert spaces. Then obviously I can't think of them as well pairs. There's some net entanglement, but I can't think of each as some tensor product of well pairs. So I'm just thinking to make it precise, you might have to take large dimension.
Yeah. So G is playing that role.
But before we come to gravity, I'm just saying information theoretic terms.
Yeah. So whenever we're relating anything about tensor networks,
large but not asymptotic.
Yeah.
Large enough.
No, to make it precise is what I mean, I don't know, it's almost bipartite. I mean,
for almost. But suppose you want to make precise statement that it's exactly bipartite. That could happen in large enough.
That could happen. That could happen.
Oh, you mean like being able to write down a state like that? Just
okay. I mean, of course, we can just have a dimension for Hilbert.
Yeah, exactly. Exactly.
I'm just saying, if we want to make the almost bipartite motion.
Yeah, so you want some epsilon parameter that's controlling that almost, and I'm saying that G is the parameter that controls that. On the gravity side, and here, like whenever I match tensor networks to gravity, there's an analogous parameter which is the bond dimension, which is controlling 1/g basically.
That's what.
Yeah.
There's the
yeah.
Some of the dimensions goes into the bipartite, mostly bipartite answer, and a little bit maybe that can be some.
I'm sorry. Yeah, go ahead.
Thank you. Okay. Also, wait. Yeah, there's some other applications of tensor networks to holography that I won't be discussing. For example, there's this discussion about complexity, there's non-isometric codes and black holes, corrections to the quantum extremal surface formula. These will be stuff I won't discuss, but I'm happy to discuss it later if anyone's interested. So.
And will this give an alternate picture of the state?
Not yet. It's still, I think it's still a pretty complicated thing. So that's the thing. So for general Hilbert space dimensions, we have very little idea of what the possible classes of states even could be, except the Bell pair state. Like that's the one which exists for all dimensions. And so this was a very nice conjecture in that sense. Like if this was true, it would be very simple. It just turns out to be not so, and then we don't know much about other things. Okay, good. So let's start with the reflected entropy. So the reflected entropy is defined after considering the canonical purification. So the canonical purification is where you take a density matrix on a system, a bipartite system AB, and consider the square root of that and think of it as a state. So this is probably pretty familiar. This is the same process that takes the thermal state to the thermofield double. You just think of the operator in terms of a state in a doubled Hilbert space where you have the Hilbert space on AB and another doubled copy A star B star. This is a proper purification. The square root ensures that it's a proper purification of the original state. And then the reflected entropy is pretty simply defined as the entropy of region AA star in this particular state. So this state lives on these 4 parties. We just pick AA star and compute the entropy in that. This was a quantity that was defined by Datta and Faulkner in the context of holography, primarily motivated by finding something that has a nice holographic dual. It hasn't been studied nearly as much directly from the information theory side. But it still has some interesting properties, one of which is this continuity bound. So as I was saying earlier, the entanglement entropy has this nice property that if states are closed, then the entropies are also closed. The Renyi entropy does not have that property, but the reflected entropy does have this property. So in that sense, it's sort of a probe measure where you can disturb the state a little bit, but that doesn't change this measure of entanglement much. So this was a useful fact to disprove this mostly bipartite conjecture. Yeah. Yeah.
The remedial question. Why is it that rho minus this one guy is the right distance?
Yeah, so rho minus sigma, the one norm is the right distance because this is the one that ensures that all correlation functions agree to close approximation. If you do 2, so there is still a bound which works for finite dimensions, but they have factors of the dimension there. So these bounds become useless when you take the dimension to be large. So that's why, like, typically this is the correct norm to measure states in. Okay. Yeah. So a useful quantity to consider is the so-called Markov gap, which was defined in a paper by Onkar. Which is the difference between the reflected entropy and the mutual information. So the mutual information is another measure of bipartite entanglement, which also captures classical correlations along with quantum correlations. So it's capturing some aspect. The reflected entropy also captures both classical and quantum correlations, but in a different sense. So these are different quantities in general. And the difference between these you can actually rewrite as a conditional mutual information. So the way to think about a conditional mutual information is roughly that it's the correlations between regions A and B star, which are sort of invisible to B. So if you're given information of B, what's the correlation between A and B star that you still don't know about? It's sort of the thing that's invisible to B. And this thing you can show is always positive, assuming the mostly bipartite conjecture. This actually becomes 0. So for the Bell pair type state, this Markov gap vanishes.
Sorry, you said it right.
Yeah. So this thing, this one, right?
The one on the left.
Oh, this one. Oh, this is the mutual information. So the mutual information is a linear combination of entropies. It's just entropy of A plus entropy of B minus entropy of AB. Yeah.
The right-hand state of Omkar's, I didn't really say invisible, is some precise, I guess.
Yeah, I mean, this is just a heuristic way of understanding it. Like, this is the number. This is just some linear combination of entropies. Like,
again, it's linear combination.
Yeah. It's basically the difference between mutual information of B star and B star, AB star.
Oh,
like
B star?
Mutual information of A with B star B and mutual information of A with B star. So, okay.
So in a sense, you can think of it as how much of the entanglement between A and B star goes beyond.
Yeah, exactly.
That's one. I mean, if that helps. Yeah.
Okay, good. So an important point is that this Markov gap vanishes for these mostly bipartite states. So this will be an important probe for probing the question of what the tripartite entanglement structure really is.
So that the Markov gap vanishes
for the bell pair. So for the mostly bipartite state. Yeah.
State with GLC.
It also vanishes for GHZ. But yeah, that's true. There are others. It's not like these are the only. I'll tell you exactly which states it vanishes for. Yeah.
Not the W.
Not for the W state. In fact, so as I said, like this quantity was mostly motivated from the holography side. Information theory people usually care about a particular inequality to say that something is strictly a correlation measure, which is that the correlations, this measure should not decrease under, so the correlations between region A and BC should strictly be greater than the correlations between A and B. Like including another system should not decrease your correlations. But very recently, there was a paper by Patrick Hayden, John Source, and Lem, which showed that there are in fact counterexamples where the opposite happens. So this is not strictly a correlation measure. However, if we work at the classical level holographically, there is this reflected entropy, as I'll tell you, will be related to some area in the bulk, and you can show that it's a correlation measure using the classical version. This is similar to the monogamy of mutual information. So monogamy of mutual information is this story where if you use the Ryutakinagi formula, you get inequalities which are stronger than than arbitrary quantum states give you. So it's some sort of special class of states. So in a similar sense, like this inequality is also something that's satisfied by the classical part of the state, but then the quantum part will violate it.
The Markov gap is a correlation.
The Markov gap, I don't think. I think you need. Is it a correlation measure? I don't think it is.
No. The Markov gap is a difference of two relations.
Yeah. I don't think there's any reason for it to be.
I think you said that holographically you do expect this to be a correlation. Sorry, classically you do expect it to be a correlation.
Yeah, so in the sense that when I say classically, I just mean holographically at the classical level.
Okay.
Yeah.
Because their counterexample is classical.
Yeah, I don't mean classical in the sense of the system being classical, like the holographic dual being classical. Yeah. Okay, good. So in what sense is this Markov gap a measure of tripartite entanglement? So you can show that H of AB is 0 if and only if the state is a direct sum of these triangle states. So remember that the mostly bipartite conjecture was about any of these triangle states, which are bell pairs between A and C and B and B and C. And then you can also take a direct sum between them. When you take a direct sum, let's think about what the canonical purification does. So the canonical purification traces out C and replaces it with its dual partners A star and B star. So you, instead of a triangle, you get this square. And just heuristically, you can see that the correlations between A and B star all pass through B. So there's no correlation between A and B star that's invisible to B. So that's a heuristic way to understand that the Markov gap should be 0 for these states. And this is the most general class of states for which the Markov gap vanishes.
Addition of states.
Addition of orthogonal states, which don't overlap with each other. Like, for example, the GHZ state is like 0, 0, 0 plus 1, 1, 1. That sort of thing.
Okay. And what is that diagram? If you have such states which are the direct sum.
Yeah.
Then starting from this, you construct your reflective stuff by tracing over.
So we traced out C and then we purified it in this canonical way.
Right. Okay.
And
you purified it like that.
Yeah.
and then all the entanglement between A and what was it, B star?
Yeah. Yeah, exactly. Between A and B star goes through B. Exactly.
What about A star as an entanglement?
It is. I mean, this was just one way of writing this thing. So all I need to check for the Markov gap is whether this thing vanishes. Yeah. I mean, this is just some heuristic thing I'm telling. Like, yeah. Good. So yeah, as you were saying, like, not just these triangle type states are ones for which Markov gap vanishes. There are also things like GHZ states which do have tripartite entanglement for which the Markov gap also vanishes. Nevertheless, what the bit threads picture says is stronger. It just says that the state is roughly one of these states, in which case you do expect that the Markov gap so it's a prediction that the Markov gap should vanish in holography as well as in random tensor networks, which are basically some toy models of holography. So that's the prediction of that conjecture. And that's the thing that we want to disprove. Okay.
Sorry, just to understand this.
Yeah.
So that's a prediction, but if you were just a low level whatever physicist, and all you knew was the Ryu-Takayanagi formula, could you check this conjecture on the gravity side?
Just the Ryu-Takayanagi formula? Well, yeah. I mean, you want the holographic dual for the reflected entropy, but once you have that, then yeah, that's what I'm going to do.
Okay, that's what you have. Yeah, that's what
I mean, generalizing the reflected.
Oh,
yeah.
So in this conjecture, they don't attempt to make it for multiple parties, saying that mostly bipartite.
There is a 4-party version of this, which is that it's mostly bipartite plus a perfect tensor. You need a perfect tensor because, yeah, I mean, this is still a very special kind of state. This is all they needed to saturate. I mean, it had enough parameters to give you the right entropies, and it saturated, like it satisfied MMI and everything. So it was a nice thing they conjectured. I don't have much to say about that yet.
But it doesn't work for 3, I mean.
Yeah. Yeah. Yeah, that's right. Oh, yeah, that's right. So the 4-party thing implies the 3-party thing. So, yeah. Good. So now let's talk about holography. So in holography, in the same paper by Datta and Faulkner, it was proposed that the reflected entropy is equal to twice the entanglement wedge cross section. So this is some generalization of the RT formula, which Omkar was talking about, which is, so you take some state, let's say we have these 2 intervals A and B, you look at the connected entanglement wedge if they are in the connected phase, and you look at the minimal cross section, which splits it into 2 parts. This is what we define as EW of AB. And twice of this is basically supposed to be the reflected entropy. And just geometrically, it's pretty straightforward to see that this implies that the Markov gap vanishes. For example, here, the reflected entropy is measured by twice of this area, but the mutual information is some linear combination of the RT surfaces themselves. So they're totally different surfaces. It's easy. It's similar to these other entropy cone inequalities. You just do some cut and paste and show that it has to be the case that this is not equal to 0. I mean, it's greater than 0 in general, and like generically, it just is not 0.
In the case of the eternal black hole,
yeah,
what you're doing is taking the sphere on the 2 sides,
yeah,
and breaking it up into, let's say, northern and southern hemisphere.
Yeah,
A
yeah.
And A star and B star is
the
corresponding thing, and you're computing the intent
of A star.
A and A star.
Yes.
But doesn't then that Ryu-Takayanagi surface have to go and hit the boundaries on the 2 sides? You're saying it's just the area of this thing sitting in the middle.
So that one does, but
So sorry.
no. So in that particular example, it does. And it does because, I mean,
Even in that example, I didn't quite understand.
so that example is that you have,
Because picture, right?
sorry?
This picture.
No, it's slightly different. It's the opposite of this picture. It's opposite of this picture in the sense that A and B are on one side and A star and B star are on the other side. It's the opposite of this picture.
The definition, right? Because you did A and A star.
No,
That came from that, right?
I mean, this picture is this picture, but I think he's asking about a separate case where it's like a sphere on one side.
Yeah. I was thinking of the one example of this.
One example of this is what you said. Yes, yes. Yeah. And it is what you said, like it will be the RT surface that goes all the way to both ends. Yeah. It's just that in this case, it doesn't.
I mean, what is the reason? Is there a proof?
Yeah, so I'm going to get to that. Yeah. So the arguments for this duality, firstly, is that it satisfies the same inequalities to some extent. I'm just getting to this. I'll just get to this. So firstly, it satisfies some of the same inequalities, except like some extra ones like this extra inequality that I told about. But apart from that, there's a plausible geometry that you can write down for this double state, which is the following. So you take this geometry, you look at, so the region AB is dual to this blue patch, which is the entanglement wedge of AB. And the doubling procedure basically wants to reflect across the RT surfaces. So you take two copies of this blue patch and glue them on each other. So when you have this one disk and another disk that you're gluing together, you'll get a cylinder, which is this picture. Does that make sense? So the dotted line here is the throat of this cylinder.
So we're taking a spatial slice.
This is a spatial slice. So the spatial slice is, so this gray thing is like two copies of the blue thing with the RT surfaces sitting here, which go all the way to the boundary. And in this case, because AA star is just one separate asymptotic boundary, BB star is a separate asymptotic boundary, the entropy of AA star is computed by some finite quantity which doesn't go all the way to the boundary. It's just the cross section. And just matching from this is just two copies of that original cross section, and hence this factor of 2 here.
This is a smooth geometry.
This is a smooth geometry you can write down. Yeah. Smooth. I mean, it depends on what you mean by smooth.
Doing that on surfaces of zero extent.
Yeah, it solves the constraint equations because of that, but it's not smooth in the sense like if you had a shear or something, then there'll be a discontinuity in the shear.
Oh, so not all derivatives are.
Not all derivatives, just because of this fact that like when you approach it, I mean, yeah, you're gluing things. So
is that allowed in gravity?
It'll solve the constraint equations.
What's called the eighth derivative constraint equation?
Well, it depends on what you want. I mean,
I mean, you generally try to avoid this.
I mean, you could smear this out and things like that. Like, I mean, it's in a distributional sense.
Where does this come from?
Is there a source?
Yeah.
Oh, where does this come from?
There's a lot of this way just throwing things at you.
Maybe you'll explain this, but you can derive this geometry from a reference.
Yeah, I was getting to that.
Okay.
That's how, okay, good.
This is not the BTC geometry.
I don't think this is the BTC. Maybe in ADS3 it is. Maybe in ADS3 it is the BTC geometry. I think you're right. Yeah. Yeah.
So I didn't quite understand that there's still some discontinuity. So this is just
that's a special case, like the shear vanishes in the vacuum. So, but in a generic situation, there'll be discontinuities in the shear.
But you're happy to live with sort of kinky geometries in the bulk.
Yeah.
the quantum corrections, right? Even without
No. Even without that, like there's a classical jump in the shear. I mean, that classical jump in the shear is supported like by a delta function in the Weil tensor. I mean, we live with delta functions all the time. Like, I don't see a big problem with it. Like, thin shell approximations are also just that.
Delta functions are something creating a delta function.
There has to be a legitimate source.
Oh, well, I mean, the canonical purification is creating the delta function. I don't see why that's an issue.
At least when you double the thermophile double and you go to the double sided double, there's no.
Yeah, that's right.
There's no sources in the sense of a matter source.
I mean, then you have a legitimate solution to Einstein's.
Yeah.
I guess the question you were asking was, is that true here? Do you have a legitimate solution?
It is a legitimate solution. I don't.
It will work a legitimate solution to Einstein's equations once you take 8 derivative corrections, right? I mean, it will not be near to one because you get infinities. Because if you've got
but
derivatives diverge, I mean, we tend to avoid discontinuities and non-analyticities for that reason.
But when we typically talk about the initial value problem, like we allow for data that's not necessarily smooth.
That's like very classical gravity.
Oh, yeah, sure.
Suppose we're in string.
Okay.
We know that there is a four-derivative connection.
Yeah.
If that blows up at that point, we worry.
Oh, yeah. Okay, that's fair. I mean, what I was talking about right now is nice in Einstein gravity. In high derivative gravity, you have to worry about it. You'd probably have to
I'm so sorry, but generally in ADS CFT, the usual nice rule is that you're allowed to do singular things on the boundary, but by the time you reach the bulk, it's smooth. Every time you got something non-smooth in the bulk, it's just my personal. For instance, the replica thing is very non-singular on the boundary. It's very smooth in the bulk. And the guy who tried to make it non-smooth in the boundary, maybe for side, got it wrong, right? So you should worry. Seriously. Maybe it's right for something, but
I mean, I think I agree with you that like when you take high derivative corrections into account, then you'll need to, I don't know, it'll be some smeared out version of this. It won't be precisely this, but
maybe completely different.
Well, I mean, do you believe in
proof? Then I'm happy.
Oh, if you're happy with that, okay. So let me just get to that. So I'm not going to prove it by a replica trick, but there exists a replica trick proof. I mean,
proof you believe.
I'll tell you, there are some subtleties with the proof. There are some subtleties with the proof, but the proof will essentially land you on this geometry. That's the takeaway.
The toilet with that.
Sure. Yeah. Okay. I'm not sure if I should wait. Okay.
So, sorry, maybe we'll say the separate.
So good. So the replica trick way of doing this is to try to. So firstly, we want to prepare the state, which is square root of rho AB, and then we want to compute the nth Renyi entropy of that state. Now, we don't know how to prepare a square root. So instead, what you do is prepare the state, which is rho to the m/2 for even integer m. That's something that you can prepare by a replica trick. And then we can compute the nth Renyi entropy at integer n. That's also something we know how to do. And so the reflected entropy with these indices mn it's what we call the m, n Renyi reflected entropy, is something that you can construct just by a path integral. Now, again, in order to analytically continue this, so eventually what we want to compute is the n and m to 1 limit. And you want to do some sort of analytic continuation to be able to do that. The way Faulkner and Datta did this was to first consider analytically continuing in M. When you analytically continue in M, when you take M to 1, you basically land on this geometry. And then they just thought of computing the Renyi entropy as computing the RT formula on this particular geometry that you have. The RT formula naturally lands you on the entanglement wedge cross section. But the important thing was how to prepare this state. And that was by analytic continuation, just in the same way as Lukowitz and Maldacena. Maybe I should say that again. So what I was saying was the replica trick way of doing this is we consider preparing the state rho to the m/2 with even integer m. That's something we can do a path integral for, and we eventually want to continue m to 1. Now, when you do that, this calculation, let's say you're computing the norm of this state, then this calculation is just computing the Renyi entropy. So it's just trace of rho AB to the m. We know how to do that. We do it by Lukowitz-Maldacena. We know how to analytically continue that. You analytically continue that, and you land on this geometry. That's where this came from.
Just make sure you're finally trying to get to the reflected entropy you defined earlier. Right?
Yes. So that reflected entropy will be when I take both m and n to 1. So basically, what these guys did was compute what the geometry is at given m, and use the RT formula on that geometry. The RT formula will land you on this cross section on the mth geometry. And then you just take m to 1. Eventually, you land on this geometry. So you're computing the RT formula in this particular geometry, which is the same as twice the cross section.
And finally, you were interested in the mutual, was it the mutual instance?
The Markov gap. So Oh, sorry, for the reflected entropy, we're just interested in the entropy of A star.
Oh, the total entropy.
Just for the entropy, yeah. So that's why the entropy of these is just given by this RT surface. Okay. But there's a subtlety. So this replica trick is subtle. I mean, we deal with this all the time. Like whenever we want to analytically continue, it's just some ansatz that we make and we hope that it's right. So the problem with this one, which was pointed out in this paper, was that there's an order of limits issue when you take M and N to 1. The issue is if you, so the way in which Datta and Faulkner did it landed them on the cross section, but there's another way of doing the analytic continuation, which gives you something more like the mutual information. And so you really need to determine what is the right analytic continuation in holography in order to get the reflected entropy.
If you don't mind, let me understand this A star.
Yeah.
So I've got, let's say, a sphere on which my field theory lives.
Okay.
A is some region of that, some little patch of that sphere.
Yeah.
A star is an equivalent patch.
Okay.
And then on the field theory side, I'm putting A and A star together to make some TT kind of TT kind of field theory surface, right?
Yeah.
So it's a field theory defined by a slightly singular
manifold.
Manifold, fine.
Yeah.
Okay. And on what state is that? Now that is put on some state. The field theory is put on some state.
So you start with some state. Let's say you start with a vacuum state in this case, and you picked A and B to be some intervals in the vacuum. So it's in that state.
Okay. And so everywhere apart, away from the edge, that state seems well defined. And is that state very clear where you do this, where you're putting these things together?
You mean at these edges?
Just in the field theory. Yeah.
Yeah, at these edges. Yeah, there is an. I mean, so here what we're doing is, so when I write all of this, like rho AB really doesn't make sense, right? Like in field theory, rho AB is something that's singular already.
Really singular.
Yeah.
You chopped it at that intersection of A.
Yeah, I mean, the density matrix doesn't really exist because of UV issues at the edges. But what is true is that you can work with a more careful, like algebraic QFT version of this. And there is an analog of this square root rho AB state, which is well defined.
But I need to know, I mean, before I start doing ADS CFT, I need to be told what state my field theory is.
Yeah.
So how do you start doing some Lukowitz-Maldacena without?
I mean, in Lukowitz-Maldacena, we do the same thing. Like Lukowitz-Maldacena is also singular at the endpoints, just because of the same reason.
At finite end, Lukowitz-Maldacena is okay, it's true. It's true.
On the boundary. Yeah. Yes. On the boundary, I mean.
Yes.
So it's singular for the same reason.
Path integral between there on a singular.
On a singular manifold, it's the same here.
I see. So you're saying this is a Euclidean. I see.
This rho AB to the M over 2 is literally just Lukowitz-Maldacena, just cut in half.
No, but I was thinking that there we knew we want to calculate the rho of the vacuum state.
Yes.
Here the state itself seems funny.
What do you? I mean, rho AB is just the density matrix of the vacuum state.
No, but I'm trying to think of that A star.
That state arises from this, but I mean, the starting point was just this, and then we just apply Lukowitz-Maldacena to this, right?
Well, I'm sorry, I'm sorry to be so stupid, but this A star was where my field theory is.
That's afterwards. That's afterwards. So we start with A and B. So we start with this state.
I agree. No, but when I'm going to.
When you go here, yeah.
My field theory lives on A star.
And BB star,
and
yeah.
BB star.
Yeah.
So I want to understand that, before I understand the bulk dual.
Yeah.
I want to understand what I'm computing the bulk dual of.
Yeah. So good. So whenever we talk about states in field theory, like what we really mean is that, I mean, so these density matrices that I wanted to talk about aren't really well defined. So you need some regularization to even make sense of that density matrix itself. Right?
So you're saying there isn't a well-defined state in the Hilbert space of the field theory of this?
Eventually there is. I'm just saying that writing, I mean, it depends. So, okay. If we work with algebraic QFT, like literally never talking about density matrices, we just talk about algebras and so on, there is a well-defined state which reproduces precisely what you get from rho to the 1/2. It's like the continuum limit of what you would get if you just regularize this.
So is there a way, another way to ask perhaps, is there a way to go from the vacuum state to thermofield double state using this procedure?
Vacuum state to the thermofield double state.
So that is thermophile double, right? What should be the
This one? Yeah, it is like a thermophile double. I mean, in the specific example you said, it is the thermophile double. Yeah. So
what is the relation? In what sense is the thermophile double a purified thing of the vacuum?
In what sense? What do you mean? The answer that square root of rho AB is the thermophile double is not good enough.
Is there a way to see it
explicitly, you mean?
Explicitly, that's it.
Oh.
I mean, just in the simple example where everything is.
I see what you mean. I mean, people, you can write this down in like free fermion theories or whatever, and you can see that it's a thermophile double. But
okay, exactly.
So that's yeah.
I mean, one sense in which it's doing more violence is that for the replica, standard replica trick, the deficit angle, in a sense, arises in 4-dimension 2 in space time. And here it's 4-dimension 1 that you're doing violence. Right. So you have to be more, because
it's still the endpoints of like an interval.
Yeah. Still 4-dimension 1 in space.
In space.
In space.
That's the usual story.
To me, the difference is this: that in the replica trick, you have a well-defined state.
Okay. Okay.
And then you're using a Euclidean trick to compute its entanglement.
Okay.
Here, I'm only seeing a well-defined state. Who's in that? Who's whatever.
But that well-defined. Are you happy if the well-defined state is itself prepared by a path integral?
Sure.
So that's what I'm saying. So this state rho AB. So maybe I should. So what I'm saying is that this rho AB to the m over 2 has a norm which is just trace of rho AB to the m. Okay, this is just by definition.
Okay.
So if what we usually do for this is we take, let's say, m copies. I'm just thinking of the boundary path integral. Forget about the bulk for now. So we have 4 copies here, let's say, and we just apply some cyclic. There's some cyclic path integral. There's some gluing of the different copies, which gives you trace rho AB to the m. Now I'm saying just take that state and cut it open in the middle. That's the state rho AB to the m over 2.
No, sorry, forget m over 2. I want to see the state in this field here.
I mean, this is in that field theory.
So I had a state in my original field theory.
Yeah.
It was with some degrees of freedom here, which were mixed with everything else.
Yeah. Yeah.
Similarly for A star. Now, how am I putting the two of them together to get a well-defined state on A and A star? I don't understand.
Because you're breaking the entanglement of A star.
Yes.
Now you're putting that
together in some particular.
Sorry, I mean,
I'm so sorry for being so. That's my point.
No, but I mean, maybe I'm not explaining this properly, but like this path integral, this path integral is the construction of what you just said.
I say that path integral.
So, okay, good. So this path integral is, yeah, good. So let me do that. So let's say one of these pieces was AB. So there's many copies of AB. So there's an AB here, there's an AB here, there's an AB here, and there's an AB here. There's both AB. I mean, I can't draw all of the dimensions, but there's both AB at each point. And what we did was the density matrix was prepared by a path integral, which had AB at both ends in the bra and the ket. We glued them together cyclically. Okay. And then I'm saying, so this was the example where M was 4. I'm saying just take that path integral and cut it open in the middle. That's the state rho AB squared. It's just the path integral that prepared rho AB squared, like the operator that you would have prepared, which we know how to do, but now writing it as a state.
Okay.
What type of A will come with neighbor. Right. Next time would be 8. Right.
Yeah. So here, like AB, like we basically, when we cut it open, we label one of them as AB and the other one becomes A star, B star. It's just a relabeling of that. I mean, in the other dimension, they're like together, and so it's complicated to draw, but that's the picture.
I do completely understand that you're asserting there is a state in the inverse space of the field theory on this funny manifold.
Yes.
Which one? How is it related to the original state?
It's related by this. I mean, it's the state is the square root of the density matrix. It's the canonical purification.
Okay, fine.
When you do this for this M not equal to 1, then how does this replicated geometry look like? A1, A2, A3, A4 like that?
Yeah, so this is roughly what the picture was like. So it's like A1, B1, A2, B2, blah, blah, blah. And so here, when we cut it open, we just have these bottom copies, and there's only 2 that will be open ends. Everything else is like sort of traced out. And so here in this picture, like like when you so what will happen is the brains that are so here, like in this picture, the conical defect which we do when we do Luckwitz-Mandelsena, you'll basically take like one piece of, so you can just take half of this, and there's like an opening angle here, and then analytically continue that angle. So just like Luckwitz-Mandelsena, eventually you land on this.
Just one last.
Yeah.
In my state A, I could have had a particle going like this.
Yes.
In A star, it goes like this.
Good. Yeah.
It looks singular.
Yeah. In this sense, I think it's like, well, why is it?
If it's singular, it's not a negative. I find it hard to believe this is true that it's a stable thing.
I'm not sure.
Okay,
why.
Please.
Okay, we can talk about it later. I mean, there is like a rigorous definition of this in algebraic QFT. I think, I mean, it couldn't be more in the Hilbert space if than that. I mean, even if you're not happy with the regularized version.
Discontinuous things with each other. How can that be? In fact, I am being very stupid. Please continue when I ask you.
Yeah. Okay. On the boundary, I think.
In the boundary, I agree. I mean, it's you know, at least in finite dimensions, all of this makes sense.
Yeah.
The answer clarification makes sense. In
Yeah.
the continuum limit, it sounds a bit funny.
Sounds like it could have infinite energy.
Yeah.
Okay.
And it potentially does, I think.
Okay.
Yeah. Potentially does.
So then I call that not infinite. Infinite energy. I don't care at all about infinite, but I care about infinity.
I mean, yeah, you're right. There could be shocks in the state, even in the boundary field.
Right.
But these shocks are sort of somewhat under control because you can relate them to the entropy of the original state.
Okay, but already now we're not exactly sure what we're talking about if we're talking about a state that's not in the
So you're saying that like something which that's the thing I'm confused about.
At a definite state, then we do a Euclidean path integral.
Okay.
To compute something.
Okay.
Here we started with the state that is redefined.
No, we started with the definite state here. Like
Okay, that which I understand.
Yeah.
But now some ABS here.
Yeah, and then we constructed this state using the Euclidean path integral.
No, first you need a trick. You constructed this boundary and bulk.
Forget about the bulk. Let's just talk about the boundary.
Let's talk about it.
Yeah.
So we constructed a boundary where I had this spatial section and then there was still time.
Yeah.
Okay. So on this spatial section, now we're going to try to do ABS-CFT for the boundary, right?
Yeah.
So we're trying to do it assuming there is a well-defined state.
Yeah.
Which is not the case.
But I mean,
that way, but you don't need to. I think is what Pratik is saying.
I see.
You're saying what Pratik is saying, if you should correct
Go ahead.
me, is that you can, without phrasing it that way, you can just set up the calculation of the reflected entropy in this row AB state, which you agree is perfectly well defined, as a Euclidean path integral calculation. Right? Just like your first one.
Okay. You're saying that second picture.
Yeah. You don't
forget about
that.
Okay, then I'm happy.
Okay.
Oh.
When you do some analytical simulation, you will land on the same answer.
Okay, fine. If that's the case, I'm happy.
Yeah.
I see.
Use the second picture to justify this going.
well,
It's has no end, that's why it goes there.
Well,
that's what you said.
It's a step it follows as a step.
It's a step in the process, yeah.
But the setup is clear, right?
The setup is clear, but I thought that the answer is going to come from saying that this was the boundary, and you've got all of the boundary, and therefore the surface goes inside.
Yeah.
Well, it's
How does that answer in the first picture arise? The fact that it's a minimum across second.
Yes.
For that, you need it.
This is the right for it.
Right. So I think you should say, but it's like you apply replica trick to this path integral that you've set up for rho AB, and you find you assume that there's a replica symmetric saddle and so on.
I see.
And then gravity tells you that there's a surface, which is
I see. We are not actually setting up new areas here.
no. Yeah. Sorry.
Okay.
I don't know if I meant that, but yeah, okay.
But the second diagram seems to suggest that.
Oh, you shouldn't have any heuristic pictures here, right?
Okay. So sorry.
That's fine. Okay, good. So where were we? So eventually, we want to do, like, strictly what we're doing is just doing this replica trick of this quantity. This is like a well-defined quantity in the original Hilbert space. What we want to do is then just do some analytic continuation of m and n going to 1. And we want to do this in a way which somehow explains how the subtlety of having an order of limits issue is resolved. Okay. What I'm basically going to say is, like, there's an analogous replica trick in the random tensor network. There's also going to be an analogous order of limits issue in the random tensor network, and we'll be able to see how it gets resolved. So that's sort of the key point. Yeah.
This order of limits issue, isn't the reflected entropy defined as the Rayleigh entropy of the purified state? So shouldn't you take m going?
It is. I mean, so when you have like finite dimensions and stuff, you can take the order in whatever way you want to. Like, it's analytic either way. But
from the definition, there is one particular order.
I don't think so. I mean, you could. I could have defined this as nth Renyi entropy of rho AB to the half, or I could have said like entropy of rho AB to the m over 2. Both of those, I mean, analytically continuing either of those gives me the reflected entropy. In a finite dimensional system, that would work. Either of those would work. Does that make sense? Okay, good. Fine. So, reminder of what you learned yesterday about random tensor networks. What we did was pick vertices which were Haar random states, pick many copies of them to do the replica trick. The advantage of having these Haar random states was when you average over these Haar random states, you get a sum over permutations which live in the symmetric group on n elements. And suppose we were computing something like the entropy, we're computing trace rho to the n. There's a replica trick way of computing this. So we apply some twist operators on the boundary, and those set boundary conditions for a sort of Ising partition function, which has degrees of freedom gx, which live in the symmetric group, and they have an energy function which is weighted by the bond dimensions, log of the bond dimensions, times the Cayley distance. The Cayley distance is the measure of distance between these permutations. So that's sort of a reminder from what we did yesterday. Now let's talk about the same thing in the context of reflected entropy. Okay, so the reflected entropy replica trick works in the following way. Since we wanted to compute the nth Renyi entropy of rho AB to the m over 2, there's two different non-trivial permutations that we need to apply. So firstly, we're just tracing out the region C everywhere. So we just act with the identity on C. So we're just tracing it out. Then what we want to do, so the way we've organized these elements is to have m of them living in each of these circles, and there's n of these different circles. So on the B side, what we want to do is, in the state, we want to compute the state rho AB to the m over 2, which is, you can think of half of this circle as preparing the state rho AB to the m over 2. And then we trace out the B region. So we basically glue the top half with the bottom half in each of these n cycles for B. But on A, we then apply a twist operator. So we want to measure the entropy of AA star, which means that we take the bottom half and cyclically permute it and glue them in this sort of diagonal fashion. Maybe that was too quick, but what's important is that there's a well-defined replica trick which has these specific permutations that you need to apply to compute this quantity. It's slightly more complicated than the entanglement entropy, but it's tractable. Good. So then, as we saw before, the RTN, like the random tensor network partition function, is just computed by this Ising partition function, which is a sum over these permutations with these boundary conditions. And now we can write down the naive saddles. So the naive saddles are the replica symmetric saddles.
So the Ising model is on what group now?
It's on the symmetric group of mn elements, m times n. So the naive saddles are the replica symmetric ones. So we have boundary conditions which are GA on A, GB on B, and identity on C. So the naive thing to write down is just have domains of GA, GB, and identity in the bulk, which give you one connected saddle and one disconnected saddle in this example. If you do this, this calculation is actually pretty similar to what you get in the vacuum state in ADS-CFT, and you run into the same order of limits issue for this, for the same reasons. And so the question is, how do we fix this? And in the random tensor network, there's something you can locate, which is there's a particular missing ingredient. And this missing ingredient is an extra permutation element that we call X, which lies sort of between the GAB elements and the identity. So on a Cayley diagram, the way to think about it is you have the identity, and the Cayley diagram basically measures how many transpositions you need to do to go from one to the to go from one element to the other. So you start doing transpositions, you hit this element X, which is this particular element. So it's basically gluing each of the halves together, but then they're all decoupled. You hit this element X, and then you have to, it's sort of a fork. You have to then choose whether you want to couple these circles from bottom to top or diagonally, because GB has them coupled bottom to top and GA has them coupled diagonally. So that's X is the fork at which you have to digress. And then you can eventually get to GB and GA. And you can measure the distances between each of these elements. So it turns out that this was actually the only missing ingredient. We can actually prove, and it's a little bit of an involved proof, and I don't know if I'll even talk about it, but you can ask me about it. You can prove that these are the only 4 elements that you need for the dominant saddle everywhere in the phase diagram. So you can look at arbitrary points in the phase space, and it's guaranteed that the dominant saddle will always be a configuration which only ever involves domains of these 4 elements. So the missing ingredient was this extra permutation X. So
What is the phase space?
The phase space, I just mean like if you change the size of the intervals or whatever. Like, so basically what this says is like arbitrary networks, arbitrary regions. Like that's what it means.
Even multiple intervals.
Even multiple intervals, whatever, anything. Good. So as an aside, I should say that we can do better in simple networks. Like if you just have a single tensor or a few tensors, you can also work across the phase transition. Like you can do this thing called the resolvent trick and analyze what happens across the phase transition. But here I'll mostly be talking about just regions away from the phase transition, where we already had this order of limits issue away from that phase transition. So this resolves that issue. Okay, so the general structure of the saddles is as follows. So we have some domain of identity, which goes and sits at the RT surface. So this surface that I've drawn is the RT surface for C, or equivalently AB. And then you jump into a domain of X, and as expected in the naive saddle, there are domains of GA and GB which are anchored to A and B respectively. But now they meet at sort of a tri-way point, a point where these 3 intersect. The tensions in these branes are n times m minus 2 for this brane that sits on the RT surface, 2 times n minus 1 for the cross-section type surface, and n for these other surfaces which split X from GA and GB. So putting all of this together, you can compute the Mn reflected entropy to be equal to twice the area of this tri-way cut. So this tri-way cut is defined as the configuration that minimizes the sum of these three areas weighted by the appropriate tensions up to some normalization, minus some factor that comes from the RT surface itself. So this is sort of a rigorous demonstration of what the the integer saddles are in the random tensor network. Yeah, there's a minus sign because of the normalization. So basically what happens is there's a plus n times m minus 2 contribution that comes from here, but the normalization has a minus n times m minus 1. And that's where it comes from.
I think maybe I should know this, but how do you read out these tensions?
These tensions come from the distances in the Cayley diagram. So the distances are basically the tensions. Like, because if you remember, the cost in the Ising partition function was the Cayley distance. So the Cayley distance is like the tension there. It's like the energy cost of that domain involved. Yeah, you can check this, but yeah, I mean, I'm just stating it. Good. So firstly, we see that this problem doesn't have any M dependence. Like the M dependence was naively there, but then it cancels out in the normalization. And so if eventually this thing, like the tensions in this tri-way cut don't depend on N, as you can see, and nothing here depends on M. So this problem is actually independent of M, but there's a subtlety, which is that you have to work at M greater than 2. The reason is the following. The tension here is n times m minus 2, which becomes negative when you go to m less than 2. And now, instead of trying to minimize the area, it actually wants to maximize the area. Right? This is basically the source of the order of limits issue. So if you look at the phase diagram looks like the following. So in the mn diagram, if you look above m equals 2, the problem is m independent. So you just get some domains which don't depend on M. They're just flat in the M direction. They depend on N. And they're the usual form where they have GAGB and some X regions in the middle. This was something that was not, the analog of this was not considered in the ADS safety case. So that was the missing thing. But when you go below M equals 2, because of this negative tension, there's no reason for this X to exist anymore. Now the tension would, now this brane would try to hug the tri-way cut itself. Those regions vanish, and so below m equals 2, you're left with the naive saddles again. And we know that the naive saddles led to this order of limits issue. The way to see it is this blue domain is like the connected saddle, this other domain is like the disconnected saddle. And n equals 1 is right here at the cusp. So if you analytically continued first, n goes to 1 and then m goes to 1, that's the cross-section answer. But then if you instead analytically continued down to m equals 1 first and then to n goes to 1, you get the disconnected answer. That's where the order of limits issue actually came from. And so now that we know what the phase diagram looks like, there's a simple way to, there's actually a way to justify precisely what the right prescription is. And the prescription is as follows. This problem of having negative tensions is actually very analogous to a similar problem that happens for the Renyi entropy. So if in the Renyi entropy, the brane tensions is n minus 1, right? If you're below n equals 1, the brane tension becomes negative. Now, if the brane tension is negative, then naively you want to maximize the area, not minimize the area. But that's the wrong answer. Like we know, you can rigorously justify, at least in a tensor network, that even for n less than 1, the correct answer for the Renyi entropy is still the minimal area surface. So the prescription to analytically continue is to start from n more than 1 and then analytically continue down. You can justify this by what's called the method of moments. It's basically like the resolvent. You resum all the integer moments and get some analytic function out of it. And that teaches you how to analytically continue. So essentially the story is similar. Sorry, yeah.
How do you know that that's the wrong?
That's the wrong answer. Like there are cases where we know this. Like for example, if you just have a random bipartite state, it's easy to just compute the entropies and see that it's always given by the minimal area. It's just a flat spectrum. We know exactly what the spectrum is. So we know exactly. So what I'm talking about, so here I'm talking about random tensor networks. For holographic states as well, there's an analog. Like for example, let's say you take the one interval in 2D CFT. We know from like the usual tricks that it's just given by whatever 1 + 1 over n log whatever, right? Even for n less than 1, there's no issues with analytic continuation. And so that's
But if you just take this cosmic brain point of
view,
there the tension does go negative.
So if you take this that cosmic brain point of view will actually give the wrong answer in this case. Like if you just think of it as an extra cosmic brain with a negative tension, then there's no controlled approximation. It just wants to go to the boundary, and that's the wrong answer. That analytic continuation fails there. This is something that's it's part of the prescription. I don't think there's any like we don't like derive it or anything, right? Like it's just some prescription they gave us and it seems to work. We justify it by checking with things. So
But away from 2D CFT, you don't have any other tools.
You can do this in like JT gravity or something, but I don't know of higher dimensional cases where we actually know what the exact answer is in the CFT. I mean, that's a complicated problem. If we knew it, then maybe we could. So the problem is exactly analogous. So again, you can justify it in the same way. You start from m more than 2. There, everything is flat. So you just pick the saddle that's relevant and then just analytically continue down from there.
No, but there the issue was approach to the point of interest.
It's the same problem, yeah.
But here your point of interest is m = 1? Or
it's m = 1, that's correct. But the
far away from that.
Right. But the problem starts at m = 2. Good. So what you can justify in this case is that even if you want to analytically continue down in the random tensor network, I'm not saying anything about holography at this point. In the random tensor network, you can rigorously justify that the correct prescription, because everything is flat in M, you just take the solution that you get and take it down all the way to m = 1.
So why is that the right prescription?
Here you can justify it. Like you just basically do a resolvent trick and argue for that. Like you're basically taking all the integer moments and then resumming them into some analytic function and showing that that's the same as if you did this. It's exactly analogous to what you would do for the Renyi entropy in a tensor network.
I see.
I don't know.
Holography, they use a particular order of limits.
They use a particular order of limits. That order of limits was to
their order of limits, then you get a wrong answer.
No, if you use their order of limits, you get the right answer.
No, but I mean, no order of limit will give you that kind of stuff.
It will. Yeah. Okay. Good. So I was getting to that, which was here. I'll get to that. I'll show you that it gives you the same answer. Yeah. So the only missing. So the thing that they had here was the naive saddle where there was no X region, right? That's the difference you're pointing out.
Their order of limits is first take m to 1, right?
No, it's m to 1 first.
So you will be that blue.
So it's in the blue region. The blue region is the naive connected saddle. It's this one. And that gives you the cross-section answer.
Yes.
And all I have to tell you is why the brown region approaches the blue thing as you take n to 1.
Okay.
Right? Good. So anyway, the analytic continuation in M can be done. So now we can just think about the reflected entropy at index n. And this function, this problem of the tri-way cut is actually analytic in n as well, right? Like everything is just some analytic function of n, and we know precisely what this means at non-integer n, this problem. But it's hard to rigorously justify that is the correct analytic continuation for the reflected entropy itself from the boundary side. But if you assume that, then when you take n to 1, what happens is this becomes a probe brane because it has a tension which is proportional to n minus 1. And so the location of these X configuration gets pulled all the way down to the entanglement wedge because it's only determined by minimizing these two surfaces. And so you get the full cross section. And that's exactly what the answer that they had.
So the X region disappears.
So the X region disappears in the limit of n going to 1.
Shouldn't we take n to 1 first rather than n?
Yeah, what this means is start with this configuration which had an m, Yeah, just find like when you find the location of this triway cut, it's going to be M independent. It doesn't depend on M anywhere. Just take that problem, find the solution of that, and analytically continue that. That's what it means. I mean, yeah. Okay.
Sorry, I'm totally confused.
Yeah, sorry.
What's the role played by X?
What's the role played by X?
At the end of the day, it does not play. That's the point.
For the reflected entropy itself, it doesn't. But for the Renyi reflected entropy, it does. And in the analytic continuation, because it plays an important role in the Renyi reflected entropies, it's an important thing for the analytic continuation as well.
Just to make sure, the Renyi reflected is, you have to take the n going to one limit of that for the reflected.
Yeah.
Okay. And so when you, I didn't follow up the details, but by the time you go to n equals 1, that X region disappears because of what?
Because this tension becomes basically zero.
Very small.
It's very small. So the location of this point, you want to minimize the sum of these areas, right? Weighted by that tension. So it's basically only these two surfaces that minimize their area. So they get pulled all the way out to this surface. And so this probe surface goes all the way from the boundary till the end of the RT surface, which is basically the cross section. I've just put the two intervals together, but
yeah. Because if you had traced over C, etc., it would have become that cross section. With that cross section, your earlier figure was where?
That cross section was here. So it started from, so this surface is the RT surface, right? So when you trace over C, this is the RT surface. So the white region is sort of deleted when you trace over C. That's probably what you mean. And the cross section goes from that point all the way till the wherever you split A and B.
That's what it was.
Sorry, but there's another function which also produces the right answer, right? Namely, the function corresponding to m less than 2.
What do you mean by the?
So for m less than
if, for example, it doesn't produce the right answers for the 1, n Renyi reflected entropies. Like this phase diagram is wrong. Is what I'm saying. You're right that you'll get the reflected entropy correct, but it's at one point. Everything else will be wrong.
If I use that, the dark
even the blue region, because you're missing this X.
And when you say you get it wrong, you check it against the actual answer.
Yeah, the actual answer from the tensor network side, like from the boundary state.
The way you do that is how? Put it on the computer.
You can do that, like we can do numerical checks, but you can also rigorously argue just analytically.
Analytically, I thought analytically is where you're getting all these diagrams.
Oh, sorry, you mean, so sorry. Is all the, well, this part, the fact that you can analytically continue in M is something you can justify rigorously. I mean, I am giving you an analytic continuation, which is just the naive analytic continuation of this problem, right? But you can justify that by this resolvent technique. So that's a rigorously justified thing. And then for the N, it's a bit of a leap of faith, but you can check it numerically. That's
Sorry, in your S or MN formula,
yeah.
The previous slide, the area of this C RT surface.
Yeah, so good. So that cancels out, and it cancels out for the following reason. So if you look at this, so this A min is normalized by dividing by this n-1 basically. So these have tensions n over 2 times n-1. And there's a factor of 2 here. So there's a plus n over n-1 coming from these two branes which hug the RT surface, and there's a -1 from this. So they cancel out. Okay. Good. Okay, fine. So I'm not going to go through the proof. What I'm going to say is the following. Is the connection to bit threads. So eventually the way we solved this problem is to rewrite this. So initially what we started with was trying to find the minimum energy configuration of this partition function, right? Like, so we were looking at the Ising spins living in the symmetric group and wanted to find the minimal energy configuration. by doing some appropriate steps, which you can ask me later about, you can basically bring it down to an integer program. This integer program is the following. It's minimizing a function. You can think of rho of E roughly as like an energy cost associated to edges with the weight, which is fixed by the bond dimensions. So it's some weighted function of the weighted energy functions on the edges, subject to these path constraints. So you have a constraint such that if you go from A to B or A to C or B to C, you at least have to cross, you at least have to have one energy cost somewhere on that path. You can kind of see how it's related to the tri-way cut problem, because essentially the tri-way cut was like, it had some tensions on these regions. And I'm specifically taking the case n equals 2, where the tensions all become equal. So it's like just a usual, not weighted tri-way cut, where they're just equally weighted.
Sorry, but here you are showing what exactly this is the tensor network or
this is tensor network. Like for this, I'm not going to say anything else about holography for the reflected entropy. Like everything is just a rigorous statement about tensor networks.
And here you are showing that in tensor network, the bit picture is not.
Yeah, and I'm telling you why.
So again,
there was
number of equations.
Yeah, it was clear from the fact that once we showed that reflected entropy equals twice the cross section, it was clear from the fact that Markov gap not equal to 0 that the bit thread like the triangle state is not possible. So that was already clear. Now I'm just trying to say like trying to get as close to bit threads as possible. So I'm trying to So this path constraint is like is basically telling you when you go from A to C, you need to cross a brane, like you need to cross a domain wall at least once. And similarly, when you go from B to C or B to A. So it's possible to show that it's equivalent, but an important thing is that this function rho of E, which basically measures the cost or the energy cost associated with an edge, is an integer. So this is an integer constraint, which says that rho of E is either 0 or 1, or it can be higher integers, but the minimum configuration will have just these. And so basically the minimal energy configuration with this integer constraint will be that it's 0 everywhere except at the locations of these tri-way cuts where it's 1. This ensures that any path from A to C, B to C, or A to B has at least one energy cost. Now, integer constraints are interesting things in computer science, like they're NP hard problems, they're NP complete problems when you have an integer optimization. And the problem is they don't have, you basically can't apply convex duality. So you can't go to a max flow version of this problem unless you relax the integer constraint. So if you relax this integer constraint, there is actually a dual bit threads picture. But what happens in that bit threads picture is now rho can be anything which is non-integer. And so the minimal energy configuration takes this following form, where the tri-way cut basically breaks out into branes that sit at the extremal surfaces. So instead of having weights 1, now they split into two things that have weight half. This happens if you relax the integer constraint. And this is precisely the triangle sort of state. So if you use this, you end up with the reflected entropy equal to the mutual information. And this would say that the Markov gap is 0. And this is the picture that the bit threads told you about. So this integer constraint, and so the fact that the minimal energy configuration of these two problems is different is what's called an integrality gap. It's basically saying that when you relax this integer constraint, you end up with a much better energy configuration. This is not the case when you measure the entanglement entropy. So for the entanglement entropy, whether or not you have the integer constraint, you just end up with the minimal surface. So you can relax the integer constraint. So when you naturally compute it from the tensor network side, you end up with a similar integer program. But the key point is that you can relax the constraint and end up with a bit threads picture. But for the reflected entropy, you cannot. So this is like getting as close to bit threads as you could.
So it's the lesson that the bit thread should be allowed to interact in the bulk.
I think, I'm not sure there even is a bit threads picture. Like, I don't know how to think of, Like there's no flow problem which will give you this integer constraint thing. So I don't know, even with interactions, I'm not sure if that can work. Yeah, there are these.
And there the dual problem is claimed to be solved by these pictures.
There's a what's the hyperthread problem actually?
So I think you let the bit thread have focus. Yeah, it can split like that. Right. So you can have
but you're saying the minimal energy configuration is this?
Piece of thread, let's say.
Yeah.
Like thread.
Yeah.
And then you try to maximize something. And then the answer
but is it like with the constraint that they have to split or something? Because this seems like a valid configuration for that as well. Like aren't bit threads special cases of hyperthreads?
No, but you allow for something more also.
You allow for more, but I'm just saying like this is a higher energy configuration than this.
No, well, okay. So in this case, there will be some number of these hyperthread have to be present.
Yeah, maybe you put a constraint, then yeah, I actually don't know about that.
Actually, no, sorry. I think you have to use you don't use bit threads for these three things. When you have three things, you have to use those hyperthreads.
You have to use the hyperthreads.
Yeah, well, if you have four things, you have to use the four hyperthreads, something like that. And then you get these pictures.
Okay, I'd like to, yeah, maybe we can chat about it. I don't know about this.
Okay.
Very quickly.
Yeah.
Sorry, what precisely the bit thread picture? Can you just one say?
Okay. So the bit thread picture was this triangle picture. So the bit thread picture was, it's slightly different from this. So the bit thread picture was not computing the reflected entropy. So I'm not claiming that. It was computing the entanglement entropy of three different parties, right? Simultaneously. And there was a bit thread configuration, which was this triangle sort of thing, which went from, which basically gave the idea that there could be bell pairs that are shared between these three different parties in this triangle form.
Mine was very, just even for maths original, even for bipartite. What was the picture?
Oh, the picture was this one. This one.
Yeah,
so the picture was, what this means is you want to consider a flow where one endpoint of the thread is in R and the other endpoint is in R bar, and it has some maximum density, and you just want to maximize the flow, the total flow.
What does that mean? Maximize the flow?
I mean, you want to maximize the number of threads going from one to the other.
Subject to the fact that the density.
Yeah. So the fact that the density is constrained tells you that basically the blocking point is this minimal area surface, and the maximum flow you can put through that is constrained by that.
These are like electric field lines?
Yeah, you can think of it as field lines. There's you can think of it that way.
And what you're saying is, okay, this kind of picture for A, B, and C isn't
it doesn't work for the purpose of, so when you start considering other multi-party entanglement measures like reflected entropy, it doesn't work. It works for the entanglement entropy of three parties.
Maybe the field lines become non-immediate.
Yeah.
Yeah, for any bipartite it works, but is that one any just for the bipartite entanglement?
For the bipartite entanglement, it definitely works. It doesn't seem like it works for this, yeah. I mean, this is sort of, I mean, we already know it won't work because of this Markov. I mean, the triangle state doesn't work because of this Markov gap, but this is just trying to say that even a bit, it's hard to even derive a bit threads picture for this.
So the lesson I'm taking away, unless there's something further, is that this bit thread thing is just useful mathematics, but it's not giving you a good picture of what's going on, right?
At least in the sense of, it's not helped with, it's helped with some other things, like it's helped with proving like entropy inequalities, for example, but it's not helping with getting a picture of what the entanglement structure is like.
Yeah, that was, I think, the real motivation behind it.
I think so. I mean, that's how I think of it.
Otherwise,
that's right. Okay. So good. So finally, there's so now, I mean, even if you don't do the analytic continuation, so you might say, oh, your analytic continuation is suspect or something. there's still the fact is still that the Markov gap can be lower bounded by, instead of considering the reflected entropy minus the mutual information, because the Renyi entropies are monotonic, you can instead bound it by the second Renyi entropy of the canonical purified state, right? So the SR at n equals 2 is lesser than the one at n equals 1. And so this provides at least a bound. And you can just show that, I mean, this problem, as we showed, was just this tri-way cut problem, which, I mean, this difference literally becomes the difference between these energy configurations. And so the Markov gap is lower bounded by this integrality gap. So the integrality gap is the ratio between the optimum energy of this configuration and this configuration. So this integrality gap plays an important role. I mean, there's a nice connection between the Markov gap and this integrality gap. And this is generic, like pretty much any graph that you write down will have this sort of difference between these two configurations. And so this disproves that version of the bit threads conjecture.
So doing this integrality gap, is that related to this number of endpoints of cross sections kind of thing?
Yeah, I thought about that. I'm not exactly sure if it does, because
in ADS, ADS3, there is.
I mean, there is an interesting connection. I mean, so this idea was in Omkar's paper, which was, it's related to this point, that the fact that you have a tri-way cut is somehow related to this tripartite entanglements, measuring that. And the number of endpoints was somehow giving you, in ADS3, it gives you a bound on the Markov gap. I think it's like the existence of these endpoints. Yeah, I don't know. At this point, I don't see a direct connection with that. Okay, let me just briefly talk about this. So here, everything was about random tensor networks. Let me just say a few things about holography. So here, the picture that we got was of these tri-way cuts. Yeah, sure.
Again, not to take anything away from random tensor, just to understand what it's adding to the discussion.
Yeah.
Suppose I was a very conservative guy, which by now you know. And I said, well, all I know is ADS CFT, and I know that you can compute various kinds of entanglement doing replica tricks on the boundary, and I know how to map boundary partition functions to bulk atom.
Yeah.
Okay, this is all I know.
Yeah.
Then couldn't I start from there, and even for your more sophisticated measures of entanglement, figure out, it seemed to me you could figure out that sometimes you have to take this cross section.
Well, you could do this. So in principle, what you could do is compute the integer m, n reflected entropies, because that's just some path integral that you have, and then you're all powerful to compute the gravitational path integral. So you can tell me what the gravitational saddles are and so on. That would be good.
So that abstract sense also meant that then you take your whatever limit it was.
Yeah. So that's where we started from. We started from the proposal that there was a specific analytic continuation that was proposed, which suffered from some problem. And there was no idea we had, like we don't have, the problem was this order of limits issue. Like, how do we know this is the right analytic continuation?
That's the right order of limits.
Yeah. Like firstly, that was one of them. And then I think also now in hindsight, it tells you that the Renyi reflected entropies come out wrong. Like those are not even the minimal energy configurations. So now we also know that.
I think this is related to the fact that replica symmetry is broken.
It's roughly that. So this X, you might think it's like replica symmetry breaking, but it's not really replica symmetry breaking, because if you look at the structure of the cycles, it's actually more symmetric than the other ones. So it's not replica symmetry breaking, but it's a new sort of gluing pattern. Like it's a different topology, which was not considered in the naive saddle.
But I mean, okay, is that the conclusion, that you should be including more than the naive saddles? But you know, you don't have to discuss anything in one's thinking. Just carefully include all possible.
So carefully include all saddles. So even once you do that, then you run into the issue of what's the right analytic continuation. Now, maybe in the context of holography, you could have had some argument. Like we usually don't have any such argument. We usually just propose something and say, oh, this gives you a reasonable answer or something. In the case of the tensor networks, you can be pretty rigorous about it and prove that that's the right prescription for the analytic continuation. And if you believe there's a connection between tensor networks and holography, you'd say, oh, this gives me some evidence that that's the right prescription for holography.
Okay, no, but where I was going was, okay, so let's say you do something with your random tensor networks,
yeah,
and you find out, okay, this is the right prescription.
Yeah, yeah.
Can you then go back and show just using ADS-CFT?
No, it's hard. I mean, it's hard for technical reasons, but it's because I'm not all powerful to do the path integral.
Okay, but one is in, but then Marderson said you don't have to be, if you just want to go to the end going to one limit. And that kind of thing doesn't work.
It's because, I mean, so even that was a leap of faith. Like Lukowitz and Marderson just gave us this rule and like, why not?
I think there's a proof. I think.
Sorry, the analytic continuation is not.
No. Right. Okay.
That's the issue.
The replica symmetry.
That's the main issue. That's the main issue.
So you're saying, okay, if replica symmetry is not broken, how do you find the relevant saddles?
Yeah, I mean, yeah.
In fact, saying even this new saddle is the replica preserving.
It's replica symmetric. It's just not the naive saddle you'd write down.
So
which was not written down. I mean, that's what I mean.
Okay, there's a well-posed problem in ADS-CFT.
Yeah.
And we don't know what is the saddle.
I mean, I think at this point we have a guess for what the saddle is. It's basically the one with this topology.
Okay, but you can't go back to the gravity calculation and show that is the saddle or that is.
So sometimes you can, and I was going to talk about one case where you can.
Fixed area states or something.
Yeah, in fixed area states, I think you can. There's a little bit of a problem because what fixed area states do is fix too many areas. So the problem is here, the relevant areas are the external like RT surfaces, which you can all simultaneously fix, but then you can't also fix the cross section. And I mean, so the tensor networks fix every possible area simultaneously. And so it's a little hard, I mean, in non-trivial networks to translate that directly to holography. You can't always do that. But sometimes you can.
So and for reflected entropy, was this red guy or the black guy correct saddle in the end?
Only for computing the reflected entropy, yes, this was the correct one.
And so say again, for what quantity was it?
It's wrong for pretty much any reflected entropy.
Meaning n equals 2, for instance.
N equals 2, m equals 2, whatever, anything. Yeah. Okay. So one example that we can actually compute in holography is the following. So a simple case. So if you remember, the tension here was proportional to m minus 2. So a case which is actually tractable is when you go to m equals 2, which is where this x drops out, and the calculation is a little bit simpler. There we can see exactly how the analytic continuation works. So this is so here we're computing this reflected entropy at m equals 2 for arbitrary n, and I don't know how much detail. So if you believe me, if you write down the path integral, what's true is that.
Very, very trusting.
Oh yeah, for sure. The boundary path integral that you need to write down to compute this quantity is actually just a torus. It actually turns out to be pretty simple. Like it's just like keeping track of the topology of the way you're gluing things together, you end up with a torus. And the picture is the following. So in this torus, the state, which is related to what you were asking before, is the following. So think of this torus and cut it open in half. Then there's some slice which lives there, which is this blue and red slice, and then the other copy of it on the other side. The outer boundary of this torus is the region A. The boundary on this side, the outer boundary on this side is A star. Similarly, the inner boundary here is B, and the inner boundary here is B star. So this state, it's like so this is the cylinder that I was drawing before. So this, it has an outer circle, which is AA star, and it has an inner circle, which is BB star. Okay. And the cross section is what is the horizon in this picture. Right. This is basically what you were saying. I mean, this is like the BTZ saddle. So now we can think about what these tri-way cuts were like. So we can think about one copy of the original Cauchy slice. So the original thing we had one copy of A, one copy of B, and two intervals which were C. So think about cutting open this torus in half, and then also cutting it open vertically. So let's cut it open in this axis, as well as on the usual way you cut open a donut. That gives you this following slice. So it has a circle. It has these semicircles which correspond to the intervals C. So the boundary, first let's look at the boundary. So the boundary is a circle which has C, then A, then C, and then B. So it's like a circle which has these four intervals. And the solution is the BTZ saddle. When you analytically continue in N, all it does is inserts a conical defect at the horizon, which controls what the opening angle is at this cusp point. So it's just the opening angle of this donut. So now what we have is there's a region of C, there's sort of a domain associated with C, which ends at a point which has an angle that's controlled by N. So that angle changes as a function of N, and then the answer for the reflected entropy is just the horizon in that solution. So it's basically what we had in the random tensor network, except now this is with full back reaction, because when you insert these branes, it back reacts on the geometry. It changes the geometry from like one BTZ black hole to another one and so on. But the picture is basically the same. You still have this squeezed version of the cross section, which meets at some angle. So something like this, where there's a cross section, but there's some pinching of the cross section, which gives you some angle at that point. So this is one example in holography where you can compute and check that it's exactly the tri-way cut. And I think I should end at that point. Maybe I'll leave this for next time. I mean, it's already 1:10. So thank you.
So it has all the singularities, this conical thing, but what was the tri-way about it?
Yeah, the tri-way is like, so if you think about starting from C, so just look at the domain of this blue, and like the region that this blue and red slice has, this conical defect, if we write it in smooth coordinates, then the way it looks is like, the cross section looks like this, right? So if this is C, then there's some conical defect there. So there's some region of this form. And then there are these two slices. So now if I open it up, it looks like this. So these are the two boundary intervals C. This is A and this is B. And there's this cusp here. And the cross section is here. So the tri-way cut is the cut which is the union of these three things. So it's this junction. Yeah.
Any further questions? Okay, now let's
Thank you.